Michael Black.
So, well, so who's seen Fast and Furious 7? It's playing in Tübingen. Not that many people have seen it. It's probably not that good. But did you notice that one of the main actors, Paul Walker, well, he died during the filming of it, and they had to replace his face throughout a good chunk of the movie. It cost over $50 million. And this idea of replacing people's faces has become really commonplace in movies. And it really became famous with the work of The Curious Case of Benjamin Button, where Brad Pitt played this character of all kinds of different ages. Now, this has become so routine that you may not even notice it. You can watch Fast and Furious 7 and not know that the face has been replaced. Now, when it comes to human bodies, the rest of the body, the story's a little bit different. Here's World War Z, and there are a whole bunch of artificial bodies here. They're partly automatically and partly hand animated, and you see them in a big crowd scene, so you never get to look at them too closely. The other time we see bodies in the movies is when they're actually creatures like the lizard here, so they're not very human-like, or when they are human-like, they're like Spider-Man. Now, probably many of you saw Gravity, and it was a really spectacular movie, and the effects were amazing. It was a largely animated movie, except for the faces. And there was this fantastic scene of Sandra Bullock floating weightless in this capsule. And for sure, this must have been computer graphics, right? She's floating weightless in outer space. It wasn't, actually. It was amazing acting and body control. She sits on a bicycle seat with one leg harnessed in, and she moves as though she's weightless. Now, why didn't they just replace her body? Like, they're replacing faces all the time. Wouldn't it have just been easy to simulate her body? Well, they didn't do it. They simulated everything else in the scene you're seeing is purely CG, except for Sandra Bullock herself. And I think the reason for that is the human body is actually pretty complex. We have about 600 muscles, a couple hundred bones, a couple hundred joints, and a wide variety of different kinds of joints. We're also very, how should I say, soft and jiggly. And so we all jiggle. And our shape changes throughout the day even. Depending on what you had for dinner tonight, your shape may be a little bit different. So our goal is to actually build digital humans that look like this, or even better than this, that wiggle and jiggle and move just like real people do. These are purely synthetic, and they don't exist yet in the movie. So I'm going to tell you how The Secret Life of Triangles will get us there. So you may not realize it, but all of these things you see in the movies are basically made of triangles, big triangulated meshes, almost everything. And so how do we deal with that? What can a triangle do that can produce body shapes? Well, the first thing to think about, triangles can't do a whole lot. Let's take a single triangle on this template mesh, this mesh here. What we can do is we can move it in space. That's 3 numbers. We can translate it in X, Y, and Z. We can rotate it around the 3 axes. That's 3 more numbers. We can scale it. That's a single number, a uniform scale. And we can shear it in a plane, and that's another 2 numbers. So that's a total of 9 numbers to describe everything you can possibly think of doing to a single triangle in 3 dimensions. Now, if I take this entire mesh and I apply just the right 9 numbers to each triangle, I can deform them and translate them and squish them and stretch them to form a new body. So that would be, that's what we've done here, transformed all the triangles in the blue ones and turned them into red ones. Now, if we want to represent the whole body, we use about 15,000 triangles. If you can apply 9 numbers to each of the triangles, that means there's about 135,000 numbers to describe the body shape of a person. Now, most of the settings of those 135,000 numbers don't correspond to people. They just choose a random 135,000 numbers. I guarantee you're not going to get the shape of a person. You're not going to get the shape of anything. So the question is, how do we tame these triangles? And that is, how do we characterize the settings of those 135,000 numbers that give me human bodies, just human bodies, doing things that human bodies do? So the idea here is we're just going to collect a whole lot of examples of human bodies, thousands and thousands of people. We all have different body shapes, and and quite a huge variety of body shapes. We're also going to collect thousands of poses, people of all sorts of ages and sizes and genders and nationalities, and doing all kinds of bending and stretching and everything the human body can do. And we do that using a special system that at Max Planck, and it's called a 4D body scanner. And maybe you can see here there's some little scanning pods. Each of these has 2 stereo cameras and a color camera. There's some also fancy lights around. And here's the 22 cameras, the color cameras shown on the left, and the 2 grayscale cameras in each scanning pod. So there's 66 cameras looking at a person, and some speckle projectors shooting out into the scene to put texture onto the body. And then a stereo system actually computes the shape of the person. This is done at 60 frames a second. And so if you look, you see fat moving. It's quite nice and mobile. This guy's fantastic. It looks almost, these are professional models, by the way. They're highly paid professionals. Don't try this at home. But look at these meshes. They're a little bit noisy. They actually have many more triangles than what I told you. We don't want this many triangles. And every triangle's in a different place. So what we need to do before we can try to analyze body shape, we have to bring them all into correspondence. And we do that by taking a template mesh, this mesh with about 15,000 triangles, and deforming it, changing the orientation of the parts, taking this pink thing and deforming it until it looks like the blue thing, which is the scan, until they look alike. And you may be able to see, some of you, that the pink thing is of lower resolution than the blue thing. Now we do that for all of the people with the same template, putting them all into alignment. And this is something we call 4CAP, which is like motion capture, or mocap. And what you're seeing here is the mesh aligned with all of these raw scans I was showing you, and it should look like it's sort of stuck on the body. So now we have the nose of every single person corresponds to exactly the same triangle. A triangle on the belly button of one person has is the same triangle on the belly button of every other person. Once we have that, we can start doing statistics. So we've got thousands of bodies, thousands of poses, all in correspondence with one mesh. And now we have 135,000 numbers for all of them. So we have thousands of these scans, 135,000 numbers per scan. We can start to do statistics. And what we do is we actually split up the kinds of deformations that can happen to the body into several different causes. The main ones being your identity. We all have different body shapes. Your pose, which has a couple of components, the rigid rotation of the body parts and the soft tissue deformation that goes along with that, muscle bulging, for example. And then the dynamics of soft tissue motion. And finally, things like breathing or aging or pregnancy. These are other effects. So let's first look at identity. Now, here, I don't know how many people know what principal component analysis is, but imagine that I have a two-dimensional data, just height and weight, and I have a scatter plot of this. I can find the mean of this, the average, and then what I want to do, what principal component analysis does, is it figures out the directions in which the data varies the most. So this would be the big arrow direction, okay? So that's a very common technique. What we actually have is not two-dimensional data, but 135,000 dimensional data. At each point in that 135,000 dimensional space is a body. We want to find the average body, and then we want to figure out the directions in that space that we all differ. So the average male and female look like this. They're constructed from about 2,000 different people each, chosen from the US and Europe. And they don't look so bad. Not too bad. But then once we know the average, we can compute how we all deviate from the average. And so each principal component I'm showing you here captures something about how body shape varies. The first couple ones capture things like height and weight. Those are the main differences. But then there's all little variations about whether you have a narrow waist and a short torso, or a short waist and a narrow torso. Here's the female ones. And with these numbers, so each of these directions provides sort of a concise way of describing a person's body. Some people are a little more on direction 1 and a little less on direction 2. And I can actually show you that. as a simple equation. So here's the average body on the left, an average man, the first three principal components, just showing you how the body varies. And I literally will take the average person, remember that's 135,000 or 15,000 triangles, and I will take 1.8 times the triangles for this weight thing, the weight principal component, then the height principal component, and then whatever the next one is. And I add those all up, and I get a human body out. And because I've built it from human bodies and done the statistics on human bodies, I'm guaranteed to get something that lives in the space of human bodies. Now, if you want to play with this, you can go to our, we have a bodyvisualizer.com website. You can load male and female models. You can have it in metric units. You can play with the body shapes, but this is a way of exploring the population. And here you could change the height and weight. You can create some sort of crazy shapes also, if you like that. Anyway, so that's something you can take home. Now, I want to show you, before we go, though, I want to show you something about soft tissue motion. So I promised that we would factor these into different components. So when we move around, our pose changes, our muscles deform, but also the soft tissue varies. On the left, you're seeing one of these scans aligned to our template. In the middle is the effect of changing your pose. And on the right is all the soft tissue stuff that happens when you move. So we build a model of that as well. It's something we call DYNA. Once we've built the statistical model of how you move and how your fat jiggles as you move, we can apply it to new people and new motions and create completely synthetic creatures. We can also take one person's jiggling fat and apply them to another person. So we could take this heavy guy, apply it to this skinny guy, and make him look like he's kind of, I don't know, really made of soft stuff of some sort. And then, and so we could do this for people, and maybe in the film industry they want to do this. And then we can do it for characters as well. So we can transform one person onto another. We can also do something fun, which is we can exaggerate the fat. So here we increase the deformations by a factor of about 2. And you see the fat guy. But one thing that's interesting is while his deformations are a little exaggerated, they're still sort of human-like, right? They're doing the right thing. So we can do exaggeration. And our soft tissue motion varies with our body shape, and particularly our body mass index. And so we build a statistical model that you see as you get heavier, different things happen to you. So now, if you've watched this whole thing and you think, yeah, that's me, come be a participant. You can come and get scanned. Email us at pstrials@tubingen.mpg.de, and I have some flyers up here if you want them. You can come and we can build a digital model of you, and you can join this vast database of used to make body shapes. So this is the work of a great big team of people. The top 2 rows are people at Max Planck, and the bottom rows are mostly at Brown and in the past, except for a couple of them. And so I wanted to thank them. And the ogre thanks you. He should be playing. That's a shame. Oh, poor ogre. Ogre seems to have crashed my computer. If your shape is changing in other ways, by the way, we're quite interested. I have a whole lot of other stuff to tell you about, but I'm completely out of time. Thanks for your attention.